Last time when we left off, we were talking about methods of approximating rate of change functions. What we're going to do today is continue with that a little bit and then talk about how to actually write some, or at least write a closed form function for rate of change for a couple of examples. Next week, that's what we're going to be focusing on the whole week, writing closed form, meaning easily to use and substitute into rate of change functions for a given accumulation function. So to start with today, we saw this was the example that was on the worksheet that I passed out on Wednesday, whatever the last class was. It was not Monday. And so we talked about on the front side or on the back side of this at the top, this graph here. If we make it an approximate accumulation function by playing connect the dots, decide a starting point, 0 in this case, and an interval width, and then connect points on the curve to one another, draw straight line segments that are easy to calculate constant rate of change for, because they are, over each straight line segment, there's one constant rate of change. We can calculate what that is approximately by looking at it, or if you had a GC file, you could do it more precisely if you knew what the formula was that was graphed here. But you can at least estimate and find those ratios, the dy's to the dx's for each of the intervals. So the thing is that when you make the intervals smaller, you get better approximations. And on this you can see I have h, I tried to make it about 0.1, but h about 0.1. See if I can get it to just a little, well, about 0.1 for h. And you can hardly see past that first interval the difference between the exact and approximate accumulation. Although the approximate accumulation is piecewise linear, has lots of little corner points in it, whereas the original was this nice smooth curve. And the rate function that we get by doing that changes suddenly. A rate that's one value then suddenly jumps to another and another and another. So it's a discontinuous rate function in small steps at a time, small pieces, in this case width of 0.1, 1/10 of a unit each. And we can make that smaller and smaller, until you can't even really see these anymore, and it just looks like a series of dots being graphed. They're really just small steps. And again, the approximate accumulation that used to be very visible as straight line segments connecting points on the exact black curve accumulation, they become kind of invisible. So this is very, very close to the idea of some exact rate function. It's not changing a lot. You can see that although this is just a sequence of a whole bunch of values, they kind of have, let me pause this when it's out here. They have the same sorts of values, like whether they're long steps or short steps, they're all in the same approximate y value location. So by making these smaller, it's making it less chunky. It looks kind of like it's becoming smoother, but it's really not. It's still a whole bunch of series of steps. So in order to write out what these rates are, what we decided then in class was for any interval, the left end of the interval is for this one, it's a 0 plus some number of delta x's, but it's the left of x for any value of x. So the approximate rate of change function for this rate number 1 here, this is method 1, that's what the subscript is. We decided that this was given by, well, we do oops, sorry about that. Let me draw a line that's slightly more horizontal. That'll probably help. All right, so I'm going to draw this first. So if I have the function value, this is function f, the function value at the left and the right ends of any interval that contains x, whatever that might be, whether x is at the end of it, x is in the middle, whatever the intervals are. And they're really tiny ones right now. They're intervals right now of 1/100th or so. So I can't draw that small. But for any x value, whether x is in the middle or the ends, what we're going to say is, well, the rate is defined by taking the value at the left and the right, drawing a straight line segment between them, doing the change in y, or the dy, dy, over the change in x, dx, that horizontal part. And so the change in the y values from one end of the interval to the other, well, the left end of the interval is f of left of x for any current value of x. For any value of x, left of x gives you the x value at the left end of the interval. F of that gives you the y value at the left end of the interval of this curve. So this was a point left of x, comma, f of left of x. And at the right end, we have the f of, well, left of x plus delta x, which is kind of a mess to write, but left of x is the left end of the interval. If I add delta x to that, I'm now at the right end of the interval. That's the y value at the right end minus the y value at the left end. And then if I do in the denominator, left of x plus delta x, not f of that, but just those x values, minus left of x. The left of x is dropout. What left of x plus something and then minus left of x is just that something, delta x in this case. Or, easier way to say that, the distance between the left and the right end of the interval is delta x because we made it so. That's how we defined it. So in any case, our rate function had this f of left of x stuff in the numerator, describing the change in the dependent variable values from the left to the right end of each interval, whatever interval x is in. This is the change between those two. So the thing is with this, and what we decided was that although that matches up with what we did going the other direction, we only ever get these kind of chunky step functions. There's no way to make them all mash back together again. I can't get these dots that it looks like right now, small steps, to join up with one another, no matter how small I make delta x. So we needed to make an adjustment to our method in order to make a continuous rate function, something where I smoothly blend from one to the other, because that's what's really happening in this. I have a very steep rate, and gradually it gets slower and slower, kind of tapers out to look kind of flat along here, not getting flatter, but this looks fairly linear out in this section, meaning kind of like the Usain Bolt graph. Doesn't look like the rate's getting a lot different, whatever rate it is. In this neighborhood, in this moment right here, it looks about the same out here, just eyeballing it. But in any case, I've got high rates that get lower and lower smoothly. They don't jump from rate to rate in reality, even little tiny jumps. So we had this second method that we were talking about at the end of class last time, where what we want to do is, instead of dividing this up into intervals and finding one rate for each interval on the accumulation function, what I want to do instead is imagine that I've got intervals of width, oops, sorry, I want to make this a little bigger so I can see it. Intervals of width, whatever, let me make this interval of width 0.4 rather. And I want to imagine looking at, as x varies, every time I change x a little bit, I'm going to change my interval. It's still an approximation because this is not whatever rate I'm going to find using this interval. This isn't an exactly linear function. So I know that this rate's going to be an approximation, but what is nice about it is if I think about the steepness of this secant line that's drawn between the 2 points, its steepness changes smoothly from a larger number to a smaller number. Well, somewhat smoothly. I can only do pixels so well. But animation-wise, as x increases, I can see that the steepness of the rate of change of this function changes smoothly from something steep to something less steep. It doesn't jump suddenly. It just smoothly goes from one to the next. So if I were to graph the y values, or the rate values that go along with this, the rate values that match the slope of that blue secant line, the change in y over change in x, for any interval here, now this is an interval of width 4. So this is an approximate rate function because for this x value right here, which is 0.53, I can see from my play button down below, when x is 0.53, I'm using an interval of width 0.4 to estimate the rate that I'm assigning to x equals 0.53. So I'm finding one rate value from this whole interval. Now I could make that interval shorter, which would give me a slightly different estimate. You can see that point at the end of the rate curve is moving a little bit upward maybe. Maybe you can see that. So maybe this would be a better estimate by having a small value of h, or using small intervals at a time. I'm going to put it near 0.1. There we go. It's about as close as I can get. So using an interval of 0.1, I'm going to get different rate values than using 0.4. Neither is quite what I'd call exact, but it's not changing a lot. And I can see that as I trace over the graph on the right, the accumulation graph, there's not a whole lot of difference between the straight line connecting the 2 points and the curve that's in reality function f. So this should be a fairly good approximation. So any position that I put x in, or any x value that I'm looking at, I can generate an approximation for what's the steepness there at x, or in the moment where x is, by looking a little bit ahead and finding a rate between those 2 points. So it's not whatever x is, I need to find the left end of the interval and the right end of the interval. X is the left end of the interval. Whatever the current value of x is, just use that as the left end of the interval. And then go a little bit ahead to find the right interval, the right side, and how far ahead? That's up to you. If you're trying to do numerical calculations, pick a number that's convenient. Like this is about 0.1, as close as I can get it. If I'm trying to make something more precise, a better approximation, I can make h smaller and smaller and smaller until I can hardly see the difference between those 2 points. Now, if you're doing this on a physical graph, it's a little hard for you to compute anything if the points are that close together. But if I'm looking at this, I can see, well, and if you notice when h is very small, the rate graph on the left, on the right, the line hardly seems to be moving. It's a little bit. But the rate graph on the left, especially near x equals 0, is either higher y values, higher rate values, or lower rate values, depending on what interval I'm using. And it's just a choice of this h in order to get an approximation. So this blue curve, although it's a curve and it's nice and connected, it still only is an approximation that gets better and better as h gets smaller. It doesn't make it exact just because it's smooth. It makes it easier to deal with because it's smooth, that's for sure. But when h is extremely small, and the smallest I have on here programmed in is 0.005, 5/1000ths of a unit, I can see that, okay, that looks fine. How do I know this is good enough? Like, it depends on what you want to do. How small is small enough? Depends on what you need to do. Now, in reality, there is a function that, here, I'm going to make h large for a minute. There is a function that's our overall goal, that's an exact rate of change function. This red curve here on the left is an exact rate of change function. And we're going to come up with ways to generate a closed form function for that using just algebra skills. Come up with a formula for, not this one in particular, but for rate functions in general, to find a closed form rate function, a usable, you can plug into it sort of formula easily, based on having a formula, a function rule for the accumulation. We'll be able to come up with rate of change functions for anything, including something that looks like this eventually. But the point of my graphing that right now is when h gets smaller in this approximation in the blue curve, you can see it's getting closer and closer to that red rate function until eventually, even at 0.005, even me staring at the screen super close, I can't see the difference between those two curves other than where they end here. So even up at the beginning here, where one was a poor approximation generally because the graph's rate changed so quickly, the f rate of accumulation was very high at first, but you can see that with h extremely small, this is essentially the same. So that's our goal, to imagine in general, if h is extremely small, I have something that's essentially the same as this mystery exact rate of change function. So we're going to come up with those, see what they get essentially close to. But just to go back, looking at this formula that I have written here, I'm going to make h large for a second so we can draw things out. Just in terms of where this comes from, it's the same idea as what we did with the left of x sort of idea when we had fixed position intervals. On this I have, at the left end of the interval here, I have my x coordinate is just x. I'm defining the left end of each interval to be whatever the current value of x is. So then the y value other half of the correspondence point would just be f of x. At the right end, all we're defining here is, okay, this is an h. I'm calling it h to distinguish it from delta x. This delta x was what we used in our one method where we had an a value, and then delta x was how far apart those intervals were, like spaced next to one another, a plus 2 delta x, a plus 3 delta x. So as not to get this confused, just using a different symbol, h, for how far horizontally we go across here, the correspondence point at the other end of this interval would have an x coordinate that's h larger, and then its corresponding y value would be f of x plus h. But again, all we're doing is finding the ratio of changes, dy to dx. So dy, f of x plus h minus f of x, over x plus h minus x, same as the denominator in the other method of calculating these. The part of it disappears, so all we have left is how wide is the interval, which should make sense. How wide is, what's the change or what's the variation in the independent coordinate? It's h. Why? Because we said it was going to be. That's how we defined this. So this gives us an approximate rate function for any value of h that we want. It could be exact if we make h essentially 0. It can't be 0. If I don't have any variation, I don't have any rate of change. If I don't change anything, there's no rate of change. But I can imagine h being essentially 0 so that for each individual moment for x, each small moment, I can assign a rate value to that. And if I make h small, as opposed to h being 0.3, you can see that this mysterious theoretical existence of the red curve, the exact rate function, I'm getting closer and closer to that just by making h seemingly small. And this is just 5 thousandths. I could make it 0.0000000005, and it'd be better than that. But visually speaking, it would look essentially the same. So the values of this with an h value of 5 thousandths versus an h value of 5 billionths is not going to be noticeably different. Just depends on what level of accuracy you need, what you want. But you can imagine, and we're going to talk about this algebraically, you can imagine h becoming essentially 0 and what patterns arise in the expressions that you get. So what I want to go to is, if you remember, we were talking about, clear this off, talking about back a while ago, the rate of change of the area of a square with side length x. And we didn't have any negatives for that, so we had y equals x squared. We just had the graph from 0 to something, so 0 through, let's say, like, I don't know, 10, so I can zoom out if I want to. But we saw this parabola function, this quadratic function here modeling x was the side length of a square, and x squared then, y represented in this graph, or the dependent variable, was the area of that square. And we talked about how we could estimate the rate of change. Let me just put this in the front. Estimate the rate of change of the area with respect to side length, or how much the area changes per incremental change in the length of the side of the square in terms of numbers. And we used for that a couple examples. We used like just intervals of width, like, 1, so 0, 0 to 1, 1, and 1, 1 to 2, 4, calculating out some points and the slopes of the lines over those two different intervals. But what if I just, instead of using those fixed intervals of width 1, let's just imagine for a minute, I have a general point on this curve. This is some mystery value of x. And I could call this mystery y-coordinate f of x, but if it's the curve y equals x squared, if this is the point x, how would I describe specific to this function? And I didn't name it as a function, I just did the simple typing. But, so not function notation here, but what would be the y-coordinate when I have x as the input? X squared, right? So what if I have another point, I'm just drawing it in a general location here, that has an x-coordinate that's h to the right of it? What would be an expression for the y-coordinate at that same point? Or what would I need to do? You don't have to simplify, just x plus h squared. Yeah, whatever the x-coordinate is, square it. That's what this function says. So x plus h quantities squared. So here's two coordinate points on this curve, and they're just generically drawn. I drew them at places, there's numbers here, but like 1, 2, 3, but not really concerned about that. If I want to describe, like we just did, this rate of change function, first of all, I'm going to call it the rate of change of function, here, let me call this f of x, which GC wouldn't graph that if I just wrote f of x equals x squared, but I'd wrote y equals. So if I want to call it function f, then the rate of change of function f I can define by doing, in general, f of x plus h minus f of x over h. And that can be approximate if h is not any particular size, or it can be close to exact, or I can assume it's exact if h is essentially 0. But with this particular function f, I can say r sub f of x is, let's see, well, here's my f of x plus h, so x plus h quantities squared minus f of x. So these are just the y coordinates, or the expressions for the dependent variable at the beginning and end of this general interval here. And then the denominator is just h, x plus h minus x is h. So here's an expression for specifically this parabola, this square area's rate of change function. This is a formula already. This is a function rule already. It's perfectly fine. It has a parameter of h in it. It's not particularly usable in its current form if I imagine h to be 0. So I would call this probably a kind of like an open form expression because of that h. If I want to think of this as an exact rate of change function, I have to imagine h essentially 0. And you see the problem with that? I've got the h denominator, and if you deal with fractions where the denominators is 0, that's definitely a problem. Essentially 0 means I'm dividing by things like 1/1,000,000th, and those sorts of values depends on what's in the numerator. So in order to make a little bit more sense of something like this, we can just do some algebra and simplify it. So this is nothing magic. This is like college algebra says, all right, I can simplify this. You know why? Because there's like terms in this numerator. I just can't see them because I have some expanding that I can do. So x plus h quantity squared, remember, means x plus h times x plus h. And there is an x squared as a part of that. There's some other terms as well. But I can subtract out this x squared if I actually bother to do the multiplication that's indicated. So this first half of the numerator, if I were to multiply that out, remember, FOIL, distributing, we get x squared plus an xh and another xh, so two xh's, and an h squared, minus that x squared, the other half of the numerator, all over h. And you can see, oh, well, I can do some simplifying, which is great, but now there's h's everywhere, which is actually good. In terms of algebra, h as the denominator of a fraction, if I'm imagining it close to 0, is somewhat of an issue. But h being everywhere in the function makes that less of an issue, because what that means is there's a common factor of h to everything in this fraction, so I can factor out an h and get rid of it, at least in the denominator, where it's just a simple h. Meaning this numerator, 2xh plus h squared, could be written as, by factoring, h times 2x plus h. And the denominator is just the single h. Remember, with algebra fun, we can reduce common factors. You can't reduce terms, you can reduce factors. But that means that this rate of change function for our particular one in a more simplified version is just this, 2x plus h over 1. Now, that looks fairly simple. And for any value of h that I want, larger or smaller, essentially 0, 2x plus h just looks like a normal sort of function. There's not going to be any issues with, am I dividing by something that's almost 0? We got rid of the division, so hey, this is great. Back to this graph over here. What this says is the rate of change of function f for any value of x is given by 2x plus h. Now, if I imagine h is essentially 0, you'll see this symbol, h, like an equal sign with a dot over it, not h equal to 0, but h approximately equal to 0. Your textbook uses this. In other textbooks, you'll see the usual wiggly equal sign. H is approximately 0. If I imagine h is essentially 0, this rate of change function is super simple, just 2x. All right, so what does that mean? The rate of change of function f is 2x at any value of x. So that means this point right here. In reality, that looks like the x value is about 1.25. So if I'm at this position where x is about 1.25, I could find the y value if I wanted to, 1.25 squared, whatever that is, 25 over 16. If I want to know the rate of change, the approximate, visually speaking, slope in this moment that I have circled, I would need to use this formula. A rate of change function tells you visually about steepness, or it tells us in terms of the square context. If the square has a side length of 1.25, then the rate of change of that side length, r sub f of 1.25, is 2 times 1.25, which would be 2.5. So at this moment, when the side length of our square is 1.25, the area is increasing at a rate of 2.5 square units per unit side length. So units are kind of weird, so I could say inches or something. So if the square side length was measured in inches, I had a 1.25 inch side on the square. The area is increasing at a rate of 2.5 square inches per inch. So let me write this, 2.5 square inches, I'll write it out this way, per inch. And it's per inch of side length, just like this is square inches of area. So again, interpreting rates, 2.5 square inches per inch. As long as I make a small change in the side length, I would expect the area to change by 2.5 times that number. So if I increase the side length by going back to chapter 1 or chapter 3 or wherever we're doing this, increase the side length by 0.05, then I would expect by a small amount of change in x, dx is 0.05, then I'd expect that the change in the area would be 2.5 times as much. dy equals mdx. Don't forget about all that good stuff. So let's see. Of course, I picked something that's hard to do. It involves a 125, but I don't know where the decimal is. 0.125 or 0.0125? Let's see. Times 5 is 12. 0.125. So the area would change by a positive 0.125 square inches, assuming I did the zeros and decimals in the right spot there. But in any case, these give us rate of change functions, as you can see, in a nice, succinct form. The rate of change of f of x equals x squared is given by this function, r sub f of x equals 2x, for any x value, whether x is 0 or whatever. This is an exact rate of change function, because I can imagine h essentially 0. If h is essentially 0, this is just 2x. 2x plus minuscule amounts. And it doesn't matter if I even imagine it to be all the way 0. That doesn't make any sense change-wise, but the closer h is to 0, the closer this is to just being plain old 2x. So that's like the overall goal of what's going on here. Let me show you some GC stuff that's related to what you're going to be asked to do in some of your upcoming Math AS assignments. By the way, there is one that's due on Monday. It's only 4 questions long. There's another one that's due the following Monday, and so forth. There's a whole bunch of iMath AS assignments that you'll see if you pull them up. They're due all the way up through the end of October is what's listed so far. But let me clear this off for a moment. All right. So we just decided that, here, let me do this function definition-wise. So we had f of x is x squared. Whether we graph the whole function or part of the function that pertains to context of a square, either way is fine. So y equals f of x. We have our parabola. Now, that's our accumulation function. What I'm going to do, and you'll see notations like this in some of the homework, it asks you to type some stuff into GC. I'm going to type some little marks in here that make GC give me two graphing windows. These little apostrophes here give us two graphing windows. The ones with the apostrophes are on the right. Now, I'm just going to type r of x because it's easier. But suppose I have r of x is that 2x that we just came up with. I want to take a look at these side by side to see what this means. Oops. There we go. And I'm going to make this one show up in blue. So we've got our red x squared graph and, oops, there, our blue rate graph. Pull this over a little bit. So this parabola only has positive dependent variable values. So f of x being the side length of a square or whatever else it is. The left side of this doesn't make sense for the context of a square. But I can see that in this red accumulation graph, I've got large amounts of something, whatever it might be, decreasing to 0, and then increasing once I pass 0 as the x independent variable value. Looking at this rate of change graph, this should look like it fits with that. You've done a little bit of matching up between look at accumulation and look at rate. If this is a rate of change graph here in blue, I can see that when x is greater than 0, I've got positive rate values matching up with when x is greater than 0, this accumulation is increasing. Or to the left of 0 in the rate function, I see negative rate values. To the left of x equals 0 in the accumulation, I've got a decreasing amount of something, a decreasing accumulation. So whether this is temperature going down and temperature going back up, and this shows how fast the temperature is decreasing, right around time 0, I can see, oh, it's changing from a decreasing temperature to an increasing temperature, so changing from negative rates to positive rates smoothly, so it passes through 0. But this is the idea of that exact rate of change function. Now, let me graph one other thing, and that's, well, we came up with this from doing an approximate rate of change. So this r of x we generated by working with f of x and f of x plus h, and then imagining h approximately 0. So if I have, let's see, g of x, I'm just going to call it something simple to name. Oops, except I got the times in there. There we go. G of x equals, and then I do f of x plus h minus f of x all over h, as long as I define what h is, because h so far according to GC is probably some number like 1. Let me give h a small value. H equals 0.05. If I ask this to graph in something that isn't that color, g of x, you can see it's right on top of this blue function. If I make, here, I don't want to make it a slider. If h is 1, I get this really poor function. If h is 0.3, I get a closer approximation. G of x is this approximate rate of change. Let's see, slider. Let's see, what do I do? 0 through, There we go. So I can make h get closer and closer to 0, and as I do so, it runs right into the exact rate of change that I made. This is a way that you can visually, using GC, help to see if you've found a rate of change function correctly. You can graph the rule that you got using, we're going to learn a series of shortcut rules. Graph what you think the rate of change function is using some shortcut rules or using some algebra. And then, well, graph it by definition. Graph it by this, our trusty definition that's always going to be right. Just give yourself a small value of h, and if it doesn't seem to match up but it's close, maybe that's a case where I need h isn't small enough. I need h to be 0.0001. Make it smaller. See if one is getting closer and closer to the other. You don't have to use a slider. You can just pick a small number for h. Yeah?
Will the r of x always be the derivative of the f of x, or is that just like a constant?
It is always. So if you've taken calculus before, you probably know the term derivative. All that means is it's derived from. A derivative is used, that term is used not just for anything that's derived from f, but it's used for specifically deriving a rate of change function from a function f. I'd say that's the derivative of f. The derivative. Derivative in math means one specific thing. It means other things in other parts of the English language, but that's why we use that word. It's derived from function f by imagining rates of change over small intervals and make that interval that we imagine rates of change for increasingly small and apply it to all general intervals, not just a specific numerical spot on the graph. So this idea of a rate of change function and your derivative mastery test, which is coming up at the end of the month, is going to be about finding the short rules without having to go through all the algebra, because there are patterns. Math is nice. If I were to change this from an accumulation function for x squared versus x cubed versus x to the fourth, they're going to have some things in common. Those are all polynomials. Polynomials have they have some standard behavior, and there's certain relationships between how the x's change in those. Also things like logarithmic functions. If I change the base on a logarithm, well, every one is going to kind of have something in common. So by types of functions, you're going to take a look at how do these rate of change functions for log functions turn out? What about for exponential functions? What about for trigonometric functions? Well, there's 6 trigonometric functions, and each one's a little different, but they're all related. So you're going to learn these by type of function. We'll go over why these work in class, as well as practice using the just jump straight to the rule, because there's a portion. This is the portion of the class where a part of it is kind of like the learning your times tables in elementary school. I want you to learn it so you can do it fast and not have to do it from scratch every time. But there is a way that these don't just come from magic. So I don't just want you to just memorize these and that's the end of the story. We're going to figure out why these are the way they are, how it relates to everything else we've learned, and make sure we understand what it is we're doing, not just here's a bunch of things to memorize, end of the story. So there is going to be a considerable amount of time starting like all of next week. We're going to be looking at how do I come up with these formulas, and then we're going to practice making them for other related functions. But let me just show you as an example. One of the other functions that we saw a volume of a sphere, because I want to point out another GC computation. There was one of the animations we saw was, and let me just make this bigger. This is Word. I don't know why this window is stuck someplace where I can't move it. Well, wherever it is. We had a volume of a sphere that we were talking about, and we were talking about the volume accumulating as the radius grows. So let me just say V of x, x representing the radius of a sphere, is given by 4/3 pi x cubed. So if I wanted to represent the rate of change of that volume of a sphere as the radius increases, maybe you know what this is based on previous calculus things, but what I want you to think about is, well, this doesn't come from magic, it comes from our rate of change formulation. So I can imagine if I were to graph this, 4/3 pi x cubed is another polynomial, but between any 2 points, I can imagine that x comma f of x, or v of x, I guess, and something that's h units to the side of that, x plus h, and v of x plus h. And think about the rate of change of this function v, just in general, by thinking, let's see, well, it'd be most generically v of x plus h minus v of x over x plus h minus x, which is going to be h. So the dy over dx, the change in the vertical or the change in the dependent quantities divided by the change in the horizontal or the change in the independent quantities of this volume function. So this is giving me the rate of change of the volume with respect to radius changes, change in the length of the radius. So cubic inches per inch, or whatever measurement units you want to use, cubic millimeters per millimeter. But if I want to write this out slightly more specifically, I could put, if I define these things and put them in GC, it would graph this for me, as long as I defined what H was. So I could look at a picture of this graph, y equals r sub v, if you want to get into typing subscripts, of x, have it graph that for you, and you can see what it looks like. But we can come up with a closed form rule for this with slightly more tedious algebra, which I want to help you figure out how to eliminate, by using the specific function rule for v. So I've got 4/3 pi x cubed. That's v of x. The leading part of the numerator here is v of x plus h. So just keep in mind that's 4/3 pi times, this means replace the independent variable there, x, with x plus h. So I'm going to have 4/3 pi times x plus h quantity cubed, minus 4/3 pi times plain old x cubed, v of x, all over h. And there's a couple things about this. First of all, that 4/3 pi shows up twice in the numerator. If you want to factor that out before doing anything else, you can. But this is, as I said, this is something that would count as a rate of change function. It's just not exceptionally usable if I imagine, well, what happens as h gets exceptionally small? Again, we run into this, well, it becomes essentially division by 0, which I don't know how to think about what that's going to look like. So let's simplify this algebraically instead. And simplifying this algebraically is a little bit more messy. That we had x plus h squared. This involves distributing 3 times, well, 2 pairs of binomials, 2 binomials together, then multiply on the third. Or let me point out something in GC that's actually pretty useful. Well, there's lots of things in GC that are useful, but let me close that. And new GC window. Not that big, though. All right, so in GC, there's a lot of math things that you can do, and one of them is x plus h cubed. I can expand that. So if I select this and go to the math, one of the options here, which you may or may not be able to see because I wrote over it, says expand. There's also a keystroke for it. But bang, there it is, all multiplied out for you. It's very good at doing stuff like that. You can also solve equations by dragging things around. It's kind of fun. But like, oh, good. Now I have that x plus h to the 3rd power multiplied out. I don't have to remember binomial theorem or take some time to do this by hand or have it memorized or anything else. Like, oh, perfect. So now that's done. Let's get back to business. So this numerator, there's a 4/3 pi times all of that, x cubed plus 3hx squared, 3h squared x, and h to the 3rd power, minus 4/3 pi x cubed. And it's all over h. And without distributing here, I can see that this entire term is going to, if I were to distribute, get rid of this with the 4/3 pi on it. And so what remains is 4/3 pi times these other 3 things, each of which has an h in it. Just like the last time, only messier, we can factor out an h, and I'm just going to leave that 4/3 pi factored out as well. Factor out an h, and then we'll be able to reduce. So this is just algebra. As I said, it's not fun algebra. I mean, maybe you think this is fun. If you do, great. There's a lot of fun for you. But 4/3 pi and factor out an additional h, and we have 3x squared. If I factor out h from this term, I have 1h remaining. And if I factor out h from this term, I have 2 h's remaining, 2 factors of h, that is. And it's all over just h. So what I have by the time I'm done is, I'm going to write this over here, a more simplified form, r sub v of x, is, I've got 4/3 pi times 3x squared plus 3xh plus h squared. 3x squared, 3hx, and h squared. So we could distribute this and simplify, but one of the things is this still involves this h. H could be relatively large, and I could call this an approximate rate of change function for the volume. Or I could imagine h essentially 0 and say that's an exact rate of change function for my volume. So at h essentially 0, this r sub v of x, an exact version of this, becomes 4/3 pi times, well, let's see what's left. If h is essentially 0, h squared is even smaller. So that's definitely going away. So this is like a plus 0 at the end. If h is essentially 0, I've got 3 times extremely small thing times a mystery value of x. Not quite as clear that that's going to be 0, but I can make h as close to 0 as I want. I can make it extremely close to 0. So if I do that, both of these terms that still have h in them, this one maybe obviously is going to be extremely small. This one, there's still an x in it, so it seems like it could cause a problem. But in reality, the h can be as close to 0 as I want, so it can always be closer to 0 than x is far from 0, if that makes any sense. Like if this is a million, I could make this smaller than 1/1,000,000th, for instance. So these other terms, I can essentially say that both of those are essentially 0 as h becomes closer and closer to 0. So all that's left is this one. 3x squared isn't affected by the size of h. It's just 3x squared. And I could simplify this, call it 4 pi x squared, which if x is the radius of a sphere, 4 pi x squared, if you remember geometry, should seem like some other formula. What's 4 pi r squared for a sphere, if r is the radius? Does that sound familiar? Surface area. So the rate of change of the volume of a sphere in simplified form would be 4 pi x squared. This is just unsimplified in terms of canceling a 3. Either of these is equally usable, but why I wanted to point this out, this 4/3 pi, those multiply on, last time we just had a plain old x squared, and we came up with 2x as that rate of change function. This one wasn't just plain old x cubed. It had a 4/3 pi multiplied onto the front. The rate of change function also has this 4/3 pi multiplied onto the front. It's just that it happens to simplify with what remains. So this 3x squared comes from the rate of change of just the x cubed part. The extra coefficient, because of how algebra works, just ends up still being a coefficient. Just we can simplify when we have multiple coefficients at the end. But why does this look like a surface area formula? It's not just a coincidence. If you think about it, this is the rate of change of the volume with respect to the radius. If I increase the radius of a sphere just a little bit, it's going to be a little bit bigger all around. So what I've essentially, if you can imagine, like if you had a gumball and you just put an extra layer of candy around the outside, that's the surface area that you've just appended to that. By making the radius a tiny bit larger, the thickness of that layer of candy that you just put onto the outside of it, you've got a slightly more volume. How much larger is that volume? Well, it's larger, but like that amount of surface area you've just increased by. It's related to that. So it's an extra shell of stuff around this that's all volume. It's a change in the volume, but that's why it's related to this surface area formula. If you can imagine just putting a little bit extra on this outer layer of a sphere. But in any case, the rate of change of the volume of a sphere is given by 4 pi x squared. Not necessarily a fact that you have to remember in those terms, but things to think about. We had this f of x equals x squared, and the rate of change of that function f was given by, in exact form, as h becomes essentially 0 to x. The rate of change of a volume of a sphere, volume happened to be 4/3 pi x cubed. The rate of change of that volume in terms of the side length or with respect to the, or radius length, with respect to the radius length was 4/3 pi times 3x squared. If you can see the power function part of this, x squared, and there's a 2x, x cubed, and there's a 3x squared. What we're going to talk about next week is more details of this, but there's something called power rule. If I have some general function g of x is x to the 7th power, the rate of change of function g is going to have a power that's 1 less x to the 6th, and we'll talk about a little bit more why next time, and a coefficient that it didn't used to have. X squareds had a 2, x cubeds had a 3, x to the 7th, going to have a 7. It's one of these nice patterns of polynomials that has to do with expanding binomials. So, in any case, I have one thing for you before you leave. There's a take-home quiz this weekend that relates to our two methods of finding rate of change functions, the fixed interval method and the sliding nice smooth sequence method. So don't leave without one of these. I'll put the rest of your homework, which it does include the previously promised answers.
I mean, not like brains, but like these and stuff. Oh, like this. Oh, okay, yeah, I get off. Or no, wait, no. Maybe that's. Yeah.
See something better back to you.